So, welcome everybody. I'm going to present Around the Virtual World, Infinite Walking in Virtual Reality with Electric Muscle Stimulation on behalf of my colleagues Max Pascher and Stefan Schneegas. So, virtual reality allows us to enter worlds that may be of infinite size, like shown in this picture. But how do we get around? Currently, we can use controllers to move around, but this might be bad for immersion or can negatively influence motion sickness. So there are a couple of movement examples in virtual reality. For example, we could teleport. We're pointing to a specific direction and press a button and get teleported there instantly. Or we can do, for example, walking in place. We do a walking motion and then can move forward. But what about natural walking? So the problem is that the physical space is limited. We have a mismatch of VR and the space available, for example, in our lab, and sooner or later we will bump into walls like here, shown in this video. Simply, the space is not enough. So the question would be, how could we reduce the space needed for natural walking in virtual reality so that maybe in one point we can move around like in Ready Player One, where they can do almost anything in a really, really, really small space. And therefore we introduced electric muscle stimulation for infinite walking. And this works like following. In this video, we put electrodes on the sartorius muscle. That is the longest muscle in the human body. Here we attached electrodes on the left leg of the user, and when we apply energy to the muscle, the leg is turned, and so we can steer a person to the left in this example here. So this is another example from the work of Pfeiffer et al. Presented at CHI'19. They developed an on-body navigation system so they could steer people using EMS towards a specific destination. And here in this picture, the person was steered around an obstacle. And we used the same technique for our system. And this can look like, or it would look like this. So a user is walking and the leg is turned to the left via EMS, so the user would walk in reality on a circle while still walking on a straight path as shown in the video in the right corner. So we wanted to see how well this works, so we did a user study. First we built the system like shown in the previous video. And we wanted to compare our EMS approach to the state-of-the-art approach, vision shift, as a baseline. Vision shift works like the following. You would shift the vision of a user slightly to a specific direction, and then the user would, while he would walk, follow this in this specific direction, and then the virtual path would alter from the real walking path as shown in this picture on the right-hand side. We focused on steering people to the left, and therefore we implemented also a shift in our application to the left. This is an overview on the system we built. We use motion trackers to track the position of the participant who was walking in virtual reality. Therefore the participant wears a backpack that can be tracked. And to see the virtual world, we used Oculus Go as a mobile HMD. The user saw, while he was walking, this 2 rows of trees. We created a VR scene in Unity and transferred the real motion tracked by the system to the virtual world. Again, the user could only walk on a straight path, but he could look around freely to look to left or right, or wherever he wanted. To properly apply electric muscle stimulation, we used a little pressure sensor underneath the left shoe, This sensor sent a signal to a control unit, then applied energy to the sartorius muscle of the left leg. We evaluated the system with 12 participants, 10 male, 2 female, with an average age of almost 26 years. We had a tracking space of approximately 8 times 8 meters. In this figure you can see how we distributed the cameras in the tracking space, and the red path indicates an ideal maximum walking path of a user. So we had 3 conditions we wanted to evaluate. Each participant was walking for 5 minutes in these conditions. The first condition was we shifted the view by 8 degrees to the left. We chose 8 degrees to fit in our study room. We followed findings from CHI'19 et al., who did a lot of research on vision shifting technologies. In the second condition, we actuated the left leg of the user to make him to steer him to the left. And in the third condition, we combined both techniques. So we shifted the view and actuated the muscle to steer the user more to the left. So we got data on the motion of the participants. So on the left, there's a typical walking path. It is a little bit wobbly. This comes from the natural wobbling while somebody is walking. So we've moved the data prior to calculating the radius to fitting a circle into the path. Prior to bumping into obstacles, we stopped the participants and readjusted them so they don't hit walls or cameras. And after we readjusted them, they could continue walking. We removed these turning points from the evaluation because they would negatively influence the results. So we obtained, like in the middle, these slices in which we could fit circles to get the radius. So then we averaged these radii, and we received, for our implementation of the vision shift, an average radius for all participants of 6.737 meters. For only walking with EMS, we received 8.7 meters, so this was the largest radius. And for both combined techniques, we received the smallest radius, 5.48 meters. So this is an example of one participant. On the left, he or she was walking with the shifted view. So you can see it worked. You can see circles in the movement. EMS was not that good. You only can see semicircles for this particular participant. But when we combined both techniques, you really see that in this case the space needed for walking was reduced a lot compared to the other path. After each condition, after the participants were walking in each condition, we asked them to fill out the user experience questionnaire. Overall, we received good results for all 3 conditions, and we had significant difference between the hedonic quality of when we combined both techniques and each single condition. So the participants had gave positive subjective feedback. We also asked them to fill out the simulator sickness questionnaire. For the nausea-related score, our implementation of the vision shift was slightly worse than the other conditions. Here, EMS performed best, followed by our combination. Maybe a more subtle vision shift would lead to better results here. For oculomotor, EMS performed also best, followed by the combined approach and then the vision shift. We also conducted semi-structured interviews regarding immersion. Most participants recognized the shift, and that was not really appreciated. On the other hand, some said regarding the EMS, they didn't really feel the EMS. Some of them were really not disturbed by being actuated by the system. We also asked about cognitive demand and pleasantness, and one participant said that while he was walking with EMS, he had not focused all the time how to walk. So we concluded that EMS can guide people through virtual realities. But on the other hand, for some participants, the EMS felt unpleasant or became uncomfortable over time. Some participants reported that a combination of both techniques was less challenging than the others because they did not have to focus all the time on walking. And they appreciated that they could walk for a really long time without being interrupted from us because they did not really reach the boundaries of the room for a really long time. Okay, the take-home message would be that we developed and studied a new method for redirecting walking in virtual reality using EMS. And EMS can be used to further decrease the space needed in reality for natural locomotion in virtual reality, and especially the combination of both approaches had the best results. Thank you.
We have time for a couple of questions, so either come here or raise your hand. I'll come back here to the microphone. With the microphone.
Shadan Sadeghian, University of Siegen. Thank you for the interesting talk. I have just one question. I saw a video in the beginning of your talk showing that the participant was walking actually in circles and curvatures while the visual feedback was a straight path. The question is that don't you think that might cause motion sickness because the vestibular cues are perceiving trajectories while the visual cues are not?
Interesting question, yes. The participants in the study had not really that problem. Nobody really got motion sickness. So I think if you can walk in a natural way, this is the most significant or important part for getting not motion sickness. Is this?
One question here and then two.
Sorry.
Can I continue or not?
Yeah, sure.
But when you're actually taking a turn in a virtual world, and you actually turn your body, you feel that, and when you're not taking a turn, but still you're turning your body while seeing a straight path.
Okay, the participants didn't report that this was a problem, so I cannot say more to this. But yeah, of course, we focused here on walking straight. I think, and I actually implemented something where you could walk in every direction, but it didn't fit in the room, and then we focused on this setup. So this maybe can be something we could investigate in the future.
Can you quickly, or just briefly tell how you did the matching of turning and walking straight? I mean, you have the tracking itself is then decalibrated kind of, since you're moving on a circle.
You would calculate the speed. You track the person, and then you have the speed, and then you would put it into the virtual reality. So.
There were more questions. Okay, 1 and 2, and then.
Yeah, Aman Parnami, IIIT Delhi. Just wanted to ask if there is any constraint related to the speed of walking. Would that have any effect on a person being able to perceive the stimulation differently, or the vision shift? Would there be any effect?
Okay, we had no real delay, for example. So I think if you would walk faster, you would see a faster simulated environment. But so one participant, she was starting really, really fast, so we feared that she would bump into something. So we said, please walk slow. So we made sure that it was always a safe environment. So we did not really play around with the variation of speed, but this is something we should do maybe in a follow-up. Thank you.
Okay, I have the last question.
Yeah.
Do you think if we walk, we not only move the feet but also the whole body. Do you think that this would be stronger then? If you could actuate the whole body, what would you actuate?
Okay. Yeah, this is difficult. It's really difficult to put or to find this muscle. So whole body actuation, I think, is really difficult. To turn the whole body. That's an interesting question. Need to look into the muscles that we can use for that. Yeah.
Okay. So, but if there's one muscle you could actuate for this type of thing, do you?
It's difficult.
Okay.
You can actuate this to turn the leg, but what else would you actuate? Okay, you could actuate maybe. Oh, sorry.
No.
Try to actuate the other leg, but in this direction. So to the outside, it's easier than to the inside. That's a challenge.